Okay, thanks, Greg. Okay, the TWIB team was organized back in early of 2016, and one of the things that we wanted to do was go back and look at some of the unwarned tornado events that had occurred in recent years. We decided to choose 2014 and 2015 because they were the most current data that we had available to us, and they also leveraged the years that sales became available. So this is going to be just a general outline of the presentation that we're going to follow. I'm going to pretty much do this section one, talking about the tornado statistics and some of the radar attributes. The purpose of and motivation behind us wanting to do this is, again, we wanted to look at the unwarned and partially warned events across the central region for these 2 years. We wanted to see if there were any common elements that might have shown up or factors that might have contributed to the lack of an advance warning. In order to do a real thorough diagnosis of each unwarned tornado, there's many more factors that can be part of that process. Those we couldn't measure, so we're just looking at these in a real general sense. And the goal of the results of this was to see if there were any training needs that stuck out, and then hopefully minimize the events and improve future warning operations. So this is our methodology that we followed. The tornado tracks and information that we got from the tornadoes came from storm data, the NWS performance verification website. There was a large number of tornadoes. We went through extensive QC of the database, and there's different parts of the presentation that had varying degrees of QC to it. In general, the storm data is tracked by county segments. So we merged all those together to get complete tornado tracks. And what we ended up with was 447 unwarned tornado cases. And we're going to look at the distribution of those cases by EF scale, path length and width, duration, time of day and month. We're also going to examine any potential external factors that might have impacted the warning decision-making process, such as was there a convective watching effect, or were there prior tornadoes on that day, or was it the first tornado of the day? The other thing we're going to do is we're going to dig down a little bit deeper and look at the WSR88D data, and we're going to look at that at the closest radar to the storm that produced the tornado. We're going to look at the convective modes. We're going to look at some of the storm attributes, such as the low-level rotational velocity and normalized rotation magnitude from GR2 analysts of the parent circulation and mesovortex. We're going to look at whether there was a TDS present and the role of potentially any cell mergers on tornado genesis. All the cases are going to be stratified by convective mode. We're going to look at the distribution of that mode, the geographical distribution, EF scale, and the mesocyclone and mesovortex characteristics. And then finally, we're going to just look at whether or not sales was being used during the cases. So the last step here in the radar analysis was we wanted to look at a little bit more robust look at some of the attributes from the radar data. We wanted to look at things like the rotational velocity magnitude of the mesocyclone or mesovortex associated with it. Again, the presence of a TDS, things like that. We had to do another level of QC on this one. And what we wanted to do is also just look at the organized convective modes. We wanted to get rid of the single and the boundary landspout cases, because for the most part, there was no identifiable features in the radar data for the vast majority of those cases. So we removed all those single and boundary landspout cases. That was 59 cases. We also set a threshold where the lowest rotational velocity that we measured could be 10 knots, and that's equivalent to the NSSL MDA strength rank 1. And we removed any cases that all the V sub R values didn't meet this criteria. That only resulted in removing 2 cases. Then we removed any cases where the velocity data showed no discernible rotation, and that was 9 cases. As far as when we put together statistics for normalized rotation, we set the lowest value to normalized rotation at 0.26. And just a comment on the normalized rotation, we went with just the default settings that are available in GR2. We didn't attempt to make any changes to any of the adaptable parameters within the normalized rotation that you can. So this left a total of 340 cases, which lent themselves to more robust radar analysis. So roughly 3/4 of the original 447, we could do some more robust statistics. If we look at the tornado location versus radar range, what we found was roughly 3/4 of them were inside 60 nautical miles. The median distance from the radar was 42 nautical miles, and the median radar beam height, the center of the radar beam feet above radar level, was just over 3,000 feet. So I took all the V sub R magnitudes at the nearest tornado time and put together a scatter plot by range. And what you see here is a huge range ranging from just over 10 knots all the way up to this one that's at 75 knots. But there appears to be a clustering there between 20 and 40 knots where a large number or a majority of the cases show up. And again, I think the key thing is here is there's quite a range there between 20 and 40 knots where all these cases fall for the unwarned events. For the unwarned events with a TDS, there was a TDS present in 32% of the cases. And I should make a note here about the TDS. We looked for the 15-minute period after the tornado time to see if a TDS was present. If this was a longer-lived tornado, we didn't go beyond 15 minutes. So if it was a long-lived tornado and it ended up producing a TDS 15 minutes after the tornado actually touched down, that wouldn't be reflected in this. There was 108 TDSs present in this more robust 340 tornado data set. So that's 32% of the cases, and the majority of the TDSs occurred with tornadoes that were rated EF1. If we actually look at that, breaking it down a little bit further, what we see is the tornado strength or the rating increased, the odds of a TDS also increased with the EF1s, 39% of them, that was a TDS. The EF2s, 58%, and the only one EF3 in the case in the database, there was a TDS observed with that. So the probability, again, of a TDS increased as the tornado warning, or as the tornado intensity increased. This was a geographical distribution of those 108 TDSs, and what you see here is that land cover, and I think that's pretty much a known commodity with TDSs, appears to be a strong contributor into whether or not you're going to see a TDS a lot of the time. And as you get into the mid-Mississippi Valley or the Mississippi Valley, Great Lakes, and Ohio Valley region, where the land cover is significantly different than the plains, that you're more likely to see a TDS, especially as the intensity of the tornado increases. The last thing, sales usage. Sales was introduced in the first half of 2014, and so sales usage for the cases, the unwarned cases, there was only 83 cases that we saw that sales was on, but a lot of that could be the fact that just sales wasn't available at that time period. However, a good note is as we got into 2015, for virtually a large percentage, 91% of the 2015 sales was turned on, and it might not necessarily always have been in the right strategy as far as sales uses versus 1, 2, or 3, but it was being used, so that's a positive thing. So looking at all this data, there's a lot of different ways you can interpret it. So I'm just going to throw out some of what I thought were my key findings. Some of them are pretty straightforward. The majority of these unwarned tornadoes were weak, short-lived, and narrow. Again, that's a good thing. Most of the events occurred during the late spring or early summer, during the late afternoon or early evening. Again, I don't think there's anything really earth-shattering there. We didn't see a strong peak in the overnight hours or anything like that that you might worry about as far as maybe situational awareness. The one thing that might have stuck out a little bit was the presence or a lack of a convective watch. It may have been a factor in some cases. There was no watch in effect for over half the cases when there was the unwarned tornado was the first or the only tornado of the day. The linear modes dominated the unwarned tornado events within the Mississippi Valley, Ohio Valley, Great Lakes region, while supercells dominated the region of the Great Plains. Tornadoes rated EF1 were the most frequently observed unwarned tornadoes produced by the linear modes, whereas the EF0 tornado rated tornadoes dominated the unwarned tornadoes produced by supercell modes. And for the unorganized modes, virtually the vast majority were rated EF0. Looking at the statistics as far as radar range doesn't appear to significantly impact the lack of warning in most cases. 75% of the cases were less than or equal to 60 nautical miles from the nearest radar. Now, that doesn't mean that the best radar was being used in all cases, and we certainly couldn't sample that, but it goes without saying that you should always be using the best and closest radar to the event, or the one that has the best viewing angle when you're looking at any storm that has tornadic or any kind of severe weather potential. Looking at the VSABAR values and normalized rotation magnitudes observed with the unwarned tornadoes, we saw that there was a wide range of magnitudes observed with these unwarned tornadoes. It seemed like the majority of the unwarned tornadoes for all the organized modes occurred with VSABAR values between 20 and 40 knots, and normalized rotation values between 0.5 and 1.25. Again, a pretty big range. So thinking about the VSABAR values of less than 25 knots, perhaps tornadoes are occurring at lower VSABAR values than we normally associate with a potentially tornadic circulation. The unwarned tornadoes with VSABAR values greater than 50 knots is a bit puzzling. By any measure, it's a pretty strong circulation. Again, there's no way to know when those values existed, what was the factor that went into the unwarned tornado. Collectively, if you look to normalized rotation and the VSABAR magnitudes, they were increasing prior and up to the tornado time. But collectively, looking at all these things I've just stated in the data sets, there's no specific rotational velocity or normalized rotation magnitude that is a fail-safe indicator of tornado genesis. We're seeing tornadoes that occur with a wide range of values. So VSABAR and normalized rotation are best used to evaluate and identify trends in the mesocyclone or mesovortex strength in organization. Another product that can also help in that assessment is the multi-radar, multi-sensor azimuthal shear and rotation tracks. The majority of the unwarned tornadoes occurred with mesocyclone or mesovortex diameters less than 2 nautical miles. The tightest diameters were with the linear modes and the low top or mini supercells. The probability of a TDS increase as the tornado intensity increased. Land cover appears to be a major factor in the presence of a TDS, and should go without saying, but cell mergers should be monitored closely in any kind of warning situation. So I'm done with my portion, and I will turn it over to Rod.
Okay, so Fred went through mostly the tornado and radar attributes. I'll be covering some of these other sections. Now, the first thing we have is looking at some of the NWSCR verification statistics from 2014 and 2015. There were 631 unwarned tornado events. Now, as Fred mentioned, those are segmented, county-based. So, when we whittle down our events, is down in the 400s. In addition, 174 of those were partially warned events. And if you look at the EF scales, pretty much you can see as EF intensity increased, our skill increased with it. Now, as Fred is talking, we only had one unwarned EF3 in the database and did not have an EF4. We did have some partial warned events with those, but also remember as well that the entire tornado track is identified by the highest EF scale rating. And so, a lot of these partial unwarned areas were much weaker at the time before they hit their max intensity. So one of the issues we had going through this database was storm data quality. And it took us a long time going through all this data to actually weed out a lot of the storm data issues that we found. As you can see, we did find 29 of our unwarned tornadoes were actually warned. That's 6.3% of our unwarned tornadoes were actually warned. Now think about how those impacts of POD, false alarm, CSI. In addition, 36 more tornadoes, in addition to the 29 above, had incorrect times and or placement errors. So you add up that 36 and 29, we had 65 total errors in storm data, or 14% of our reports had errors in them. So that really, that's kind of astounding to us that we had that many errors. And there's a lot of ways that we can fix these errors. A lot of them, the time errors were often 1 to 2 hours. Storm data entry does require CST. That's potentially that maybe some of these entries are getting put in as CDT. We did have numerous events with a TDS prior to the storm data start time. At times, TDSs were also noted with no storm data. And then finally, part of our TWIP team, while it's a little bit outside of our realm, we are going to be working on with some local experts on storm data entry best practices. All storm data entries certainly need to undergo a rigorous QC process, and really don't think, tornadoes are our GIPR goals. Most offices are 50 tornadoes or under. It shouldn't be that strenuous an exercise to go through the radar data again. Make sure these reports are correct, because this is what we're being verified on. This is what Congress is seeing. So some of the unwarned tornado findings and examples. This is one example. The dot within the yellow circle, you can see is 2 hours off, 75 nautical miles from the storm. The storm's off to the southwest with the confirmed tornado warning on it at that point. And then this is 2 hours later. You can see a tornado warning is out. So this tornado warning actually went unverified. It also had, this storm was on the ground for 25 minutes. And if everybody recalls how storm data works, tornadoes are verified per minute. So that's 25 unwarned minutes that occurred with this storm. In addition, so that's the end point when it ends 25 minutes later. So that entire track went unwarned per storm data, even though it was actually inside of a warning. And that's a huge hit to our statistics with that event. In addition, we had a second tornado that occurred within that warning and a second warning that was issued. That was on the ground for 9 more minutes. So in total, we had 34 minutes of unwarned tornado warnings due to 2-hour errors in storm data. Another error, incorrect locations. The one off to the left with the yellow circle, potentially the LSR is the icon and the tornado icon, and then there's a red dot off to the northwest of that. That's actually the storm data entry point. This very well could be due to spotter location being entered and then not QC'd when it was entered into storm data. Now, all of these we went through numerous hours of storms to make sure these didn't occur with other storms, and this one certainly didn't. Everything remained off to the east with it. Another one, this is another event, and we'll see some more examples of this event a little bit later on, but you can see right now at this point, we have a tornado warning out. There is if you look at the very lower right and then the ZDR to the lower left, we do have a TDS on the storm. Notice the lowering CC to the north of that's all within the inflow region, so that's not the TDS. It's that little bit that's catching the northeast corner of that. So that tornado warning would have verified. And this storm will move off to the northeast, and we'll see what occurred with that a little bit later on. So some other factors for unwarned events. And, it looks like, we're going through all these unwarned events and factors. Now, one thing to point out is we don't know exactly what was going on in the offices at this time. What were you getting reports, et cetera. The only thing we can see is what we see in the radar data and with the reports that occurred. So, we don't know the entire picture of what was going on with all these events. But as Fred mentioned, we did have bad data due to range folding, which was 3.1% of our unwarned cases. Was that due to adaptive PRF issues? Are we in office monitoring, making sure that we are adjusting our PRF to make sure that it's correct and that we have the best viewing possible with our radar data? Are we using a surrounding office's radar? If so, and if they're not busy, maybe we can have them adjust and get better data quality with it. Also, there's several with de-aliasing issues on scans prior to the tornado. We did notice VCP and sales settings were not optimal on numerous occasions. Make sure, we did have a TWIP recommendation last year that was sales 2 at a minimum, especially for tornadic cases. And really, we recommend sales 3. Get as much data as possible, so we can see these rapidly developing situations. And a lot of these EF0s and EF1s did develop pretty quickly. So some other observations, do our warning meteorologists struggle to identify TDSs in real time? Now, I think some of this might go back to the whole fire hose of data that we have. Are we optimally looking at our data? How's our D2D set up, especially since we've gone to the 2 panel? Are we properly integrating dual pole data at this time? That's something as a TWIP team we're going to be looking at, as far as maybe having some recommended displays for these warning operations. Do we need 6 panels or 9 panels? A good 6 panel might be reflectivity, SRM, rotational tracks. You can have our ZDR, KDP, and correlation coefficient if you're in tornado mode. Warning meteorology. So, there's a lot of things we can look at there. Significant differences between local radar data and the neighboring radar. Are we looking at our neighbor's radar? Are we looking at MRMS data, et cetera, to take advantage of the multiple radars, multiple sensor data that we have? Rotation looks a lot better at 0.9 on the loft and shows up at 0.5. We've had numerous tornadoes that come close to the RDA, and I think as the longer warning meteorologists are on, as a warning meteorologist radar, they've been on for several hours. They may not be starting to look. They're starting to wear down, not looking at as much data. Maybe they start just focusing at the 0.5 data. They're falling behind and aren't seeing the 0.9 and above. So that might be the case. We had additional tornado warnings were not reissued with storms with history of producing tornadoes. In addition, we had some unwarned segments due to gaps between polygons with the inner office and polygons and at CWA and county borders as well. So we have, we're not quite reaching to the borders, and these tornadoes are moving across those gaps. So while the public may be properly warned, I guess verification-wise, we're taking hits on these. So some other observations also, obviously land spouts are difficult to detect. There was a TWIP memo set on land spouts last year. There's certainly some debate, should these be included in our GIPR goals for tornadoes, because they're really difficult for us to get. Tornadoes do occur in poor storm environments and poor storm structure and unfavorable near storm environments. So there's just some cases it's just going to be very difficult for us to get warnings out. The radar 0.5 degree beam height may overshoot primary features, and this may be more of a case for our western central region where there's just not as many RDAs in the area. And tornado warnings are issued, but a tornado occurred just outside the polygon, so maybe our polygonology wasn't quite optimal for that event. So a few stats of note: 60.7% of unwarned tornadoes occurred with a effective SIGTOR less than 1. These are all going to be excluding the boundary layers, land spouts, and singles. 43% were of the supercells were less than 1, and 73% of the QLCSs were less than 1. 71% of the unwarned tornadoes occurred with LCL less than 1,000 meters. 62% supercells were under that domain, and 82% of the QLCSs occurred with a LCL less than 1,000 meters. And then finally, 59% of unwarned tornadoes occurred with an effective SRH greater than 150 meters squared per second squared. Now, the supercell and QLCSs and actually the bow echoes were higher than that. At 62% for supercells and 67% for QLCSs. Some of the other storm types were actually lower than that, and that drug that average down. So some key findings. So we reviewed several parameters that included the sig torque calculation compared to the Thompson 2012. Overall, the supercells were compared favorably to the Thompson 2012 supercell EF0s and EF1 results, and it would help if I could not have spelling error there. Also, the QLCS's unwarned tornadoes actually occurred in more favorable environments than what Thompson 2012 QLCS tornado environment showed.